right, hello friends. So this is kind of an intro to polar coordinates for a calculus class. So let's just jump right into it. So first of all, how do we define a polar coordinate? So the idea behind a polar coordinate is that we have some point, we're going to have a fixed origin, O, and we call that the pole. And then we assume that there's some initial ray coming out of it. So we have to assume that we start here. And so where the polar coordinate comes in is from here, we define some angle theta and a radius r. And so then that gives us this point r comma theta. So this is the length of the radius, and this is the angle made with that initial ray. So first things first is you've got to get used to thinking about what this means, because this is a little different from like your normal Cartesian coordinates. So where I want to start is first I want to talk about this idea of all the polar coordinates for the point 3 pi over 4. So this is like the first weird thing with this. Okay, so initially the picture that might come to mind is, so I've got this pi over 4 angle, so here's my theta, and then I've got this length 3, there's my radius. So this might be the initial thing that you think of, but here's the deal. There are lots of coordinates that fulfill this type of relationship. So for instance, if I have r is equal to 3, what possible thetas are going to give me this relationship? Well, of course, pi over 4 will, but also you can think of rotating through here to just get back to this spot, right? And now if you think, oh, I can rotate this through and still get this same angle, that kind of changes everything, right? So how would that work then? Well, the way that that would work is, so I could have pi over 4 really plus or minus 2 pi. So right, if I go through 2 pi, that gets me back to this angle. I could also have pi over 4 plus or minus, say, like 4 pi. So really, as long as I go through an even integer of pi, I'm going to make this full rotation around. And so I can really summarize this as my possible thetas. I could have r equals 3 and then pi over 4 plus or minus 2n. 2n is what will be the way that we describe an even integer. So 2n pi. So you might be thinking, okay, great, that makes sense. We've done it. But here's the super weird thing. So you can also have a negative radius. And so this is kind of where things get weird with polar coordinates. So starting with my initial orientation here, same theta. So here's my theta still of pi over 4. So if I made this angle of pi over 4, but I had a negative radius, what I would do is you can kind of think of it as like, okay, here would be that initial angle that you need, but then you have to go in the negative direction. So I would end up shooting out, boom, this way. And so here's where my r equals negative 3 is. And so the idea now is, how could I take this radius of r equals negative 3 and rotate it back so that it still makes this shape, this relationship that I want? Because I could totally do that, right? So I think it might be helpful to think about the unit circle just to wrap your head around this. So here's our good old unit circle. And you might want to have one in front of you when you're first kind of playing around with polar coordinates and wrapping your head around this. So remember, we can kind of think of like this relationship here, this pi over 4. So kind of this arm here. So this is the arm that I would have for my r equals 3, right? So this is in the positive direction. So remember, when I have r equals negative 3, that's basically just being reflected over on the other side. So this side over here, this would represent still that angle of pi over 4, but now I have to go in the negative direction. So you see how that works? Okay, so now the idea is then, how far would I have to rotate this arm here to get back to this spot? And so actually this is the other reason why having that unit circle is helpful. So if I have r equals negative 3, what my theta would have to be is actually just this pi over 4, right? So there's this inverse relationship between the two things. So if you think about it this way, if my first angle had been theta equals 5 pi over 4, here's my 5 pi over 4, and then if my radius was r equals 3, it would be this side here. So again, if this is the side that I would get for r equals positive 3, if I want to flip it back over the other way, then I go r equals -3, and that would be my theta equals 5 pi over 4. So I think it's kind of helpful to have the unit circle in front of you when you're first wrapping your head around this, because I don't know, I think it can be a little disorienting, so I think having that visual marker is really nice. Okay, so anyways, so if my r were to equal, say, -3, then my theta would just have to be of the form 5 pi over 4 plus or minus 2n pi. Now we're going to keep exploring kind of this relationship to help you wrap your head around it, so let's keep going. So the next thing that I want to talk about is how do you graph with these like polar coordinate ideas, polar equations. So I have a handful of things that we're going to graph to try to wrap our head around it. Now here's the deal. When we think about graphing, so we actually kind of change the way that we think about our graph. And so I think about with my Cartesian system, so I have, this would be r equals, I'll label these. So this first circle, so I'm going to have r equals 1, r equals 2, r equals 3. So I can kind of think about starting from the origin and then having these different radii coming out from that circle. And so the way that you view the radius now, that is going to kind of depend on the way that the question has been stated. So to help orient you, so let's say that I have a radius of 2. So a radius of 2 and a theta of pi over 4. So here's my theta of pi over 4. And then you're going to notice I come out 1, 2. Now, if I wanted to do a radius of -2, I still maintain this angle, but instead of going now this direction, I maintain this angle, but I just go in the opposite direction, right? And that was when we had that like, and the equivalent to this side here, this would be the equivalent of having pi or theta equals 5 pi over 4. So this could be also theta equals 5 pi over 4. So I'd start from here, I'd come all the way out here to 5 pi over 4, but then my r would be equal to 2. So these two things here are the same. And then again, just to kind of round out this idea, so if I wanted an equivalent angle here, so if I had my r equals -2, then my theta would be 5 pi over 4. So again, it's 5 pi over 4 because I start here, I come around, here's my 5 pi over 4, but instead of going in the positive direction, I need to go in the negative direction. So these two things go together and these two things go together. So hopefully that's starting to make a little bit more sense of how you can relate these things. Okay, cool. So now let's play around with some graphing. So in this case, I need my r this needs to be between 2 and 3, positive 2 and 3, and my theta needs to equal pi over 4. Okay, so we can break this into pieces. Remember, I have my different kind of circles of different radii. So that idea of being between 2 and 3, that could be anywhere in here, right? So here's where my radius is 2, or it could be -2, depending on the theta. And then this other circle here, right? This is my radius is 3 or -3. So this is all my potential area that I'm talking about. And then when I think about my theta is pi over 4, this would be the angle right where I have my theta is pi over 4. Now, it's true that I could also go in the opposite direction if I had a negative radius, but I don't have a negative radius here, right? So I don't have to worry about going in this other direction. I just need to maintain my positive radii. And so what this graph is talking about is just this tiny little line in here, right? Where my radius is between 2 and 3, and I'm maintaining that angle of pi over 4. Okay, so there's one. So let's keep going. Let's do a handful of these. So now my radius is going to be between -1 and 2, and my theta is going to be between 0 and pi over 4. So my between -1 and 2, so this can be really anything. So remember, now I have to go through the 0 angle here. It could be somewhere in here, right? So this is between 2 and -1. This is kind of a mess because it depends on where our theta is. So I just kind of wanted to show you like everything that we've got to capture to get between -2 and 1. But really the theta matters quite a bit. So now in this case, I have to take in account having a negative and a positive radius. So from here to here, here's where I'm between 0 and pi over 4, right? But I also need to take that into account now for negative radii. So I also need to go in the other direction. And you can see how I've just reflected this kind of over my circle. So these are my potential areas. Now, I need only a positive radius up to 2. So here's where my positive radius would be up to 2. And then also I need my r to go to -1 on the negative side. So on this side, I need to reflect just an r of -1. So now things are kind of coming together. So from here to here, this is where I'm maintaining that theta and where my r is going to be less than 2, right? Because I have go out 1, 2 circles. On this side, my radius needs to only go up to -1. So this first circle here is the one that I need. So my final answer now is just going to be these two little sections in here. So you kind of have to like think about what makes sense for all of these conditions and like all the pieces that you kind of have to put together. But that's going to be my final answer in this case. Okay, so now I have an unrestricted r. I have no conditions on r, but my theta has to be between pi over 4 and 5 pi over 6. Now, what I would recommend here is that you try to represent that. And again, any r goes in this case. So that's kind of one of the key things that you want to think of when you draw your sketch. But why don't you give this a try, hit play when you're ready. So in this case, I have my different circles, but it doesn't really, like my r doesn't matter, right? So I can first think about just where is between pi over 4 and 5 pi over 6. So this would be the different thetas that I need if my r was positive, right? But since r is unrestricted, I also need to represent this in case r is negative. So I need to also reflect this over. And just to be clear, this will just keep going. So it's not restricted between 3. I can kind of just keep the graph going up like this and like this. But okay, so this now will reflect my desired theta for whether r is positive or negative. So that's kind of the way that we got to think through this. Okay, so I've got one more here. So what about if I just have r is greater than or equal to 1? Well, in this case, you know where that r equals 1. So you just basically need to shade everything outside of that first circle, right? So this would be the graph in the last case. Okay, so those are different ways that you can kind of graph. The other thing that sometimes you're asked to do when you're first learning about polar coordinates is to convert between polar and Cartesian coordinates. So there are a few equations that we can relate to help us do this. So those equations are x equals r cosine theta, y equals r sine theta, r squared equals x squared plus y squared, and tangent theta equals x over y. Okay, so I think it's easiest to figure out how to make these conversions by just doing the examples. So let's start by taking a couple of equations that are in polar, right? So these are all in terms of r and theta. I want to convert this back into a Cartesian equation, which would be back in terms of x and y. Okay, so I'm going to start with this first one, r cosine theta plus r sine theta equals 1. Well, the one thing that I know right from this relationship, my r cosine theta is x and my r sine theta is y. So I can just actually pretty easily make this. So r cosine theta we said was x, r sine theta, this is y. So sometimes this can be a nice straightforward conversion like this. So this just becomes x plus y equals 1 and we're done. Now let's contrast that to another situation here. So now I've got cosine squared theta equals sine squared theta. Okay. Sometimes when you have these, you might want to relate this and make a manipulation to your equation to make it a little bit easier to deal with. So I've got cosine squared, I've got sine squared. I really wish that those had an r in front of them, right? That would make my life a lot easier. It'd be a much more straightforward conversion. And so you can manipulate an equation, right, to make it what you want. So what I can do is I can multiply both sides by r squared. So if I multiply both sides by r squared, now this becomes much more clear, right? And now it's a much easier conversion. So sometimes this will work, sometimes it won't. But in this case now, this will give me x squared equals y squared. And so now we've related this back to an equation in Cartesian coordinates, so we're all good to go. Okay, and so now let's go the other direction. So what if I have an equation in terms of x, y, and I want to convert it back to polar? So I think that this is a little bit more straightforward because remember, we do have this nice conversion for what x and y actually are. So you can make that direct conversion. So for instance, if I have x minus y equals 5, I can rewrite that as r cosine theta minus r sine theta equals 5. So that is a nice straightforward conversion. Or if I had something like xy equals 2, I can take r cosine theta times r sine theta and say that's equal to 2. And so this becomes r squared cosine theta sine theta equals 2. And now I've converted it back to polar. Okay, and so I am going to leave it at that, and I will talk to you guys in another video. Bye!